House Robber 2. Let's talk about a true interview curveball. House Robber 2. This is one of the most notorious Pattern Mastery 100 problems, and it's a favorite at companies like Google and Facebook. Did you know that over 45% of candidates fail this problem in interviews simply because they overlook the circular constraint? It's a common trap, even for those who've practiced DP extensively. If you can master House Robber 2, you'll gain a serious edge in coding interviews that involve dynamic programming, adjacency constraints, or interval-based logic. Ready to level up your problem-solving game? Let's break in. Let's break the problem into its core. You have a list of houses, each with some money. If you rob two adjacent houses, the alarm goes off. And here's the twist. The houses form a circle, so the first and last are also neighbors. Our goal? Find the maximum amount you can rob without tripping the alarm. Sounds like a job for dynamic programming. But how do we handle the circle? Let's assess our options. If the houses were in a straight line, it's classic house robber, LeetCode 198. But with a circle, robbing the first house blocks you from robbing the last. So, what if we split the circle into two scenarios? Exclude the first house. Rob from house 2 to the end. Exclude the last house. Rob from house 1 to the second to last. Here's the structure. If there's only one house, return its value, no circle worries. Otherwise, solve the two scenarios. Rob houses 0 to n2. Rob houses 1 to n1. For each, use a helper function that applies dynamic programming to find the max loot. Approach: split into two linear subproblems. Time complexity, ON. This defines the solution class, the container for our code. This is the main method. It takes an array where each value is the money in a house, and it returns the maximum money we can rob without robbing adjacent houses. If there are no houses at all, we can't rob anything, so we return 0 immediately. If there's only one house, there's no conflict with neighbors, so the best we can do is rob that one house and return its value. Now we handle the key twist of this problem. The houses are arranged in a circle. That means the first and last house are neighbors, so we can't rob both. So we split the problem into two straight-line cases. This first call says, pretend we are not allowed to rob the last house, and only consider houses from index 0 to index n2. This second call says, pretend we are not allowed to rob the first house, and only consider houses from index 1 to index n1. Then math.max picks whichever scenario gives more money. Small pause. This is the smart trick that converts a circle into two lines. This closes the main rob method. This helper method solves the classic linear house robber problem from index L to index R. No circle here, just a straight line of houses. We set up two variables. Pref represents the best result up to the house before the previous one. Cur represents the best result up to the previous house. Think of it like keeping two running totals so we don't need an entire DP array. This loop walks through the allowed range of houses, from L to R, and updates our best possible robbery amount as we go. We store the current best value in a temporary variable t. This is done because we're about to update cur, but we still need the old cur value to update prev afterward. This is the core decision for each house. Cur means we skip this house and keep what we already have. Prev plus nums I means we rob this house, so we add its money to the best value that was safe to combine with it. Prev. We pick whichever option gives the bigger total. Pause. This is the main logic. Now we shift our tracking variables forward. Prev becomes the old cur, stored in t, so on the next iteration, our two-step memory stays correct. This closes the loop. By now, we've processed every house in the range. We return cur because it represents the best robbery amount for this linear segment. This closes the helper method. And this closes the class. Final wrap-up. And that's how this algorithm works. It first splits the circular problem into two safe linear ranges, then uses rolling dynamic programming to decide at each house whether to rob it or skip it for the maximum total. Efficient, simple, and elegant. Test case check. House robber 2, circular houses. Let's test our function using this input. 2, 3, 2. These numbers represent the amount of money in each house, but this time the houses are arranged in a circle, which means the first and last houses are neighbors. Here's why the solution works. Because house 0 and house 2 are adjacent, we can't rob them both, so we split the problem into two linear scenarios. Rob houses 0 through n2 that considers 2, 3. Rob houses 1 through n1 that considers 3, 2. We run the optimized rob linear DP on both segments and take the maximum. And that's exactly what our program outputs, 3. This matches the expected result and confirms the circular robbery logic is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully handles the circular constraint by evaluating two linear robbery paths: efficient, accurate, and reliable. Approach: DP with two scenarios. Time complexity, ON. This line declares the solution class. It's just the container that holds our method. This defines the rob method. It takes an array of house values and returns the maximum amount you can steal, following the rule that you can't rob two adjacent houses. This stores the number of houses in n, so we can reuse it easily instead of writing nums.length repeatedly. If there are no houses, there's nothing to rob, so we immediately return 0. If there's only one house, the best you can do is rob that one house, so we return its value. Here we create two DP arrays. Each array represents a different scenario, so we can handle special constraints cleanly. Think of it like solving the problem twice under slightly different rules. In the first scenario, we start by considering robbing the first house. So the best total up to house 0 is just the value of house 0. Still in scenario 1, by the time we reach house 1, we must choose the better of robbing house 0 or house 1, because we can't rob both. In the second scenario, we treat it as if we are not robbing the first house. So the best total at house 0 is set to 0. In scenario 2, since we skipped the first house, the best total up to house 1 is simply robbing house 1. Now we loop from the third house onward. This is a single pass through the array, so the overall time complexity is ON. This line updates scenario 1. We compare two choices. Skip the current house and keep DP1i, 1, or rob the current house and add its value to DP1i, 2. But there's a special rule here. If I is the last house, I equals n, 1, we force the answer to behave like we skipped it, by using DP1i, 1. That prevents taking both the first and last house in this scenario. This line updates scenario 2 in the standard house robber way. Either skip the current house and keep the best so far, or rob it and add its value to the best from 2 houses ago. This closes the loop. At this point, both scenarios have calculated their best possible totals. Finally, we take the better result between the two scenarios and return it. That way, we're guaranteed to follow the constraints while still getting the maximum possible money. This closes the method. This closes the class. Final wrap-up. And that's how this algorithm works. It first sets up two DP scenarios to cover different starting conditions, then iterates through the houses to compute the best non-adjacent totals and returns the best of the two outcomes. Efficient, simple, and elegant. Test case check. House robber 2 using two DP tables. Let's test our function using this input. 1, 2, 3, 1. These values represent the money stored in each house, but since the houses are arranged in a circle, the first and last houses are considered neighbors. Here's why the solution works. Because we can't rob both the first and last house in a circular street, we build two separate DP arrays. DP1 considers robbing from house 0 to n2, first house included, last excluded. DP2 considers robbing from house 1 to n1, first house excluded, last included. Each DP table follows the standard house robber recurrence. DPI equals max DPI1, DPI2, plus nums_i. And that's exactly what our program outputs, 4. This confirms that the DP table approach correctly handles the circular constraint and finds the optimal solution. Wrap-up. So, our implementation is correct. The algorithm successfully computes the maximum money that can be robbed in a circular arrangement by evaluating two DP paths: efficient, accurate, and reliable. House robber 2. Let's do a recap. Ever faced the house robber 2 problem and thought, wait, why isn't my DP working anymore? This one's a true interview curveball because it adds a circular twist to a classic. Once you learn how to handle that constraint, though, it becomes one of the most elegant dynamic programming problems out there. Breakdown recap. We started by restating the challenge: rob houses arranged in a circle, where the first and last houses are also neighbors. That means you can't rob both ends, so the problem becomes figuring out the maximum money you can take without setting off the alarm, even in this circular setup. Assess recap. We compared our options. The brute force approach would fail quickly with exponential time. Instead, we leaned on dynamic programming, but with a twist. Since the first and last houses can't both be robbed, we split the problem into two simple linear cases. 1 keycap emoji, exclude the first house. 2 keycap emoji, exclude the last house. Then we solve each one just like the regular house robbery problem and take the higher result. Structure recap. The plan was clear. Handle the edge case for a single house, define a helper function to calculate the best loot in a straight line, and apply it twice, once for each scenario. Finally, return the maximum of the two outcomes. Implement recap. We implemented this step by step, ran it on LeetCode, and everything worked flawlessly. The code executed efficiently with no errors, running in ON time and O1 space, fast and optimized for interviews. Check recap. After testing with multiple inputs, the solution passed all test cases. It handled the circular constraint perfectly and returned the expected results every time. Closing insight. The key takeaway? Complex problems often hide simple patterns. By recognizing that the circle could be broken into two linear cases, we turned a tricky DP puzzle into a clean, logical solution. Master this one, and circular constraints will never trip you up again.